Okay, so hello everyone, let's start. And what we want to say now, we want to start with some corrections to the previous time. Some discussion. So the first thing, Misha asked about examples of infinity categories, quasi-categories, and actually there is, so to say, machine for proposing examples, and it's called xinf functor, which we were discussing in the previous term, and there is a theorem that after applying this iterated x functor, any simplicial set eventually ends up to be a complex. And this is how we will be denoting the category of complexes. Basically, it is a full subcategory of simplicial sets, but I think we will discuss it later also. What else? What else? We didn't actually showed that definition of infinity groupoid admits the following, how would you say, well, what I want to say, that every morphism in a complex, when we view it as an infinity category, is invertible. So how you see that? You just take this kind of diagram and you lift it by the known properties. And how it would look like. So you get something like this, and you claim that there is such an arrow, which is something similar to if you had an inverse. So you are going from 0 to 2, and then you go from 2 to 1. Okay, and that is what you call the composition. of inverse with F. Okay, and also actually you have the inverse for F. You could see it's just almost the same thing. And what is the statement that every complex is in fact infinity groupoid. Okay, so that what I wanted to make some corrections. And now we are starting developing new things. And let's have such definition that if we have category which admits pushouts or limits of the following shape, and if you have a set of collection, okay, of morphisms, then you say that T is closed under pushouts if for all such diagrams, for all the pushout squares like this, if the left vertical arrow was in your collection, then the right one is also. Well, that is definition, and now a proposition. So let S be a collection of morphisms, and now T is such collection that it has all the morphisms with left lifting property with respect to S, which means following, that if you have such square, then there exists a lift. And so what is the statement? So then collection T is closed under pushouts. and the proof. Okay, so for proof, just so what do we get here? We are known that left one morphism admits a lifting property. Вот так все. So. Okay, so something like this. This one. This. And we want to show that the square on the right, there's a lift. Okay. What we might do, we just discard some arrows from what we already drawn, and just observe the familiar universal property.
There is a problem with the sound.
What kind of problem? Oh, sorry. And now it's better?
Yes.
Oh, I'm sorry. Well, so here we just see it's a universal by universe property of the push out. There exists canonical form, and therefore
Where is the problem with the sound again?
well, I don't know what's going on. Well, let's see. So that is all done. Okay. And another similar categorical definition. We say that one morphism is retract of another.
I think you have some kind of automatic adjustment setting.
Well,
you probably should turn off automatic adjustment of the microphone and Zoom.
So could you give me a tip? How do I do this?
Okay, so you go to audio settings. Okay.
So will we continue? One morphism is retract other morphism if there exists as a kind of diagram like this. And relations with composition of inclusion retraction are identical morphisms. Well, then we say also that collection of morphisms of category is closed under retracts if the middle one living in our collection implies that the second one is also. And now proposition similar to the one we have proven on the top, that that the collection of all morphisms sharing lifting property for any other collection is closed under retracts. And okay, also we are going to prove something like this. What we're given is that f prime lives in T, and what else? We got also such a square on the right with vertical arrow living in S, and we know that a section lift exists and want to show that such an arrow exists. Okay. How we could do this? We just could take H, our lifting problem solution to be the following composition. I'm moving to draw it here. So what we need to check, let's call it U and W. And we want to check if such inequality holds. Wait a minute. So when like this is clear, and actually what we check is this one. So we will weight this from d prime to y, and that is the same if you went like this. Well, so maybe we want to leave this kind of easy exercise. Well, then also we are almost done with this part, and another definition when category is co-complete and collection of morphism is called weakly saturated. If T is closed and closed and push-outs and retracts. Also, you actually need to ask for the transfinite composition. I'm not going to define it, but we'll tell later what does it mean. And essentially what we've proved is that when you have some collection of morphisms, then all morphisms with lifting property with respect to this collection are in fact weakly saturated. Now let's move to simplicial world and apply this machinery. So definition of trivial configuration which will denote like this. Is the following diagram holding condition. You got a boundary of any simplex. If it maps like this, and this is trivial configuration precisely if it admits a lift. This is P. And this we will usually denote like I. So proposition is that when you got a pullback square, if this morphism was trivial configuration, well, it's a pullback. Then the arrow on the left is also a trivial configuration. How do we prove this? Basically, we've been talking about pushouts some moment ago, but we could apply that theorem directly, but to opposite category. See, between in opposite category, you get pullbacks going to pushouts, and so just apply that to a cosimplicial set, and you are done. Okay. And as definition, well, Can complex is called contractible. If such a diagram holds, and here you got a point that's our definition. What we want to prove on the end of the day, so to say, is equivalent definition of trivial configuration. That we want to prove that trivial configurations are precisely such morphisms that admits lifting well right-lifting property with respect to all monomorphisms. And monomorphisms of simplicial set are just injections on any level. Some comment on this proposition might be that basically what we are doing all this time got a model category flavor, and that is true. Basically, we are just proving some results in a equivalent model structure on the category simplicial set, but not yet stating that. So how we are going to deduce that? That trivial configurations are those morphisms admitting left-lifting property with respect to monomorphisms is that we are going to actually prove yet another proposition that collection of morphism of simplicial sets is that monomorphisms is a weakly saturated collection, which also is generated by such maps. And the word generated by means that it is the smallest one containing this set. So the fact that it is weakly saturated is a just straightforward check. Check with push outs and retracts. And now we're concerned with transfinite composition. That is there's a general result that any monomorphisms can be written like this composition. So we take an image of we take an image of this simplicial set A mapped into B. We map that into such simplicial set. Basically the same set, but unioned with the deer skeleton. Then like this, with one skeleton, and so on. and the fact that our category is closed under transfinite composition is that this one, so to say, composes, if you see, and in a sense it is a limit. Maybe I should say column. And denote like that. It is now sufficient to show that any such a diagram is a monomorphism. And that is kind of now obvious if we write it like the following. In the following form. And that is pullback square. Well, because our category is closed under push-outs and actually because it is weakly saturated, then
I think it's push-out square.
what Grish?
I'm saying that I think this is not a pullback square, but a push-out square. Because you like glue cells along the boundary.
Oh yes, it is actually my miss in the notation. It's actually a push out. Okay, and now it is all okay because every condition is satisfied, and because our collection is weakly saturated, then it is just the same as stating that this map is a monomorphism, and this is I think that is easy to see, but a bit technical to prove, and you see it's quite a depressing thing to prove something in the semi-both simplicial sets, something fundamental. So we just stop here and let's recall. This collection of monomorphisms in simplicial set is weakly saturated and generated by inclusion of boundaries. to the synthesis. That's essentially what we've proved. And now we kind of able to prove this proposition about trivial configurations. Well, the proof goes like this. So what do we get here? Так. And also by previous proposition, all monomorphisms are inside T. Well, so we just got nothing to prove here. And now it is going to be a bit more fun. We deduce corollaries. Why did we care about all that? I remind, we actually end up the last time with we wanted to prove that the what did we want to prove? That quasi-categories basically admit an inner home. Okay, so we will prove that, and also we will prove that infinity groupoids is basically the same as scan complexes. We've already stated that in one direction, and that was quite a trivial, that every scan complex got every morphism invertible, and therefore it is an infinity groupoid. But the other direction is not so easy, and essentially we need to develop model category kind of thing to proceed. And let me draw something like this. The arrow on the left is monomorphism, on the right is trivial configuration. So this one exists. And the very useful result is that such a canonical map I will explain in a moment. Such canonical map is a trivial configuration map of simplicial set. So what is actually stated here? We got a fiber product on the right. So let's draw corresponding square. How that one maps, basically you take induced map from P. Well, this is P, this is I. Here you got such a map, which is a restriction. And this one object is a you say it is a pullback square. What is this canonical map? Well, it is the following map. When you take the map from B to X, so these arrows, you got following arrows. You got the restriction map here. You got an induced map here, and by the universal property, you got this one. Well, so I think there's quite nothing to prove. You got to unwind this definition in terms of lifting properties, and you just see that it is true. So what is stated again is that map of this functional complexes of U is a trivial configuration. So what we got else? Corollaries of this statement. That when we got a map like this, then for any vertex of Y, such fiber is contractible complex. Well, it's easy. Again, you draw diagram and see it. So that is also a trivial configuration over the point, so it is a contract. This set is contractible complex. Another more useful thing is that well, such a map And if you get then induced map on the functional complex is trivial configuration. That is actually extremely useful. And what we do, we just that's just a special case of a result, a previous result. You just take A to be empty set. You write all of this, and what you see that this one is a point, this one is a point, and it is equal to the following thing as desired. And I think we are ready to prove a very, very good result that if X is infinity groupoid, then it is the same as X equal with that X is a concomplex. As I said, in the one direction.
Can you move the page a bit up? I didn't.
Oh, okay. So. One direction, it is clear, as I mentioned in the beginning. And now the other direction, now this one. We take our simplicial sets to be like this. And what we've got from this kind of formula is that such set, which is by definition it is X. So you see it easily that you are multiplying point by n simplices and looking at how they map into your infinity groupoid, and that is X. That is a trivial configuration to the following thing. Map from point to point, which point times home from empty set to X, which is point basically because you got only one way to map from empty set to any other set. And then it is all over such thing that is also a point. And the whole thing is also a point. And what you see that you got for any infinity groupoid, it is trivial fibration over with the point, and therefore X is concomplex just by definition. You see. Well, let's write it down.
Clearly, not all complexes are contractible.
Oh, yes, but
This is strange.
okay, give me a moment. So we proved that.
Where did this trivial vibration in the first row come from?
You see, it is. Diagram like this, actually.
Yeah, but
So
where did the vibration X to this fibered product? Why is it trivial?
By means of the previous result, like this, and we took it as a special case. So we set A equal to empty set B and Y equal point. You know, actually, you're right. We proved that any infinity group point is contractible complex. Yes. So what I've got to admit is that it is anyway a complex, but maybe we shouldn't say that it is just any kind of bijection. So let's let it be like this, but keep in mind that we are not yet done, and I will check it later. So. In some sense, what we have left to do. What I want to do next. I want to prove the result about inner common quasi-categories. So the set of maps from one quasi-category to another is also quasi-category. So.
Вечер добрый, меня слышно? Отлично.
Bloody hell.
Ну, домашку посмотрел. Предлагаю начать с номеров, которые не получилось сделать. Заодно посмотрим и
Sorry, Rishi.
Ну, в принципе, в любом случае будет полезно посмотреть, что строим общее. Мы особо по ОДЗ еще не говорили. Сейчас, может, совместим еще с
Let's just proceed.
Okay.
Basically, what we've had in a quasi-category is that composition is, in a sense, not uniquely defined, and that triangles witnessing these compositions are also not uniquely defined, but what I want to show is that actually they form, so to say, contractible space of choices of such triangles, therefore compositions. So all, so to say, all compositions are essentially homotopic to each other. And how do we want to do this? Is by means of such theorem. And as I found out, it was a classical approach to this theorem, to this result by Joyal. And it's like that. That a simplicial set is quasi-category precisely when the collusion of Horn induces
Кстати,
induces trivial configuration on the functional complex when you take the restriction map. Okay, basically this theorem is very technical, and
So are we taking just one horn in dimension 2?
sorry, what you said?
So we consider only inclusion of horn lambda 2, 1.
Oh, yes, yes, yes. We are concerned only with this kind of horns that in a sense you could interpret that like that defining compositions are enough to some sense define a quasi-category. Maybe, I am not sure, but we are talking only about only about two horns, about special kind of horn, and make a statement about like criterion to be a quasi-category. Yes. So this proof is very technical, and I don't think we will be able to hold it, but we'll make right now some corollaries, make some use of it. Let's see, we got such morphisms in our category, and what do we have here? If we have two composable morphisms, then we could write such fiber product. That is actually we regard this as a point. I'll say in a moment. Let me draw. So that is our theorem, basically Joyal theorem, and here we got the fiber product. So what does it mean that this notation is that we taken that we are taking a two simplex defined by this composition.
Ну, то, что нельзя, надо быть уверен, что мы не произведем неравносильно преобразование. То есть, если мы точно можем утверждать,
well, like this.
вот, но тут какой момент? Это
And
будет дано по условию. То есть
so
мы не можем, по сути, наложить какое-то условие на наше уравнение. Если мы что-то говорим, тогда
that's
мы это должны
called x
выяснить.
square,
То есть,
and therefore
когда он не равен, и когда он равен. То есть, теоретически
this
это верно,
implies that
вот, но получается решение
this one
неполное,
arrow
и
is
мы
also
это уже-
trivial configuration of
Это
the
правильное
point.
действие, но нужно будет быть второе. Тогда бы это было
Well, you see it, and this implies that this one set is a contractible concomplex. So, as I said earlier, we could, if we view this space, this simplicial set as a space of compositions, then we see it is contractible space. And that is a satisfying in some sense.
Потому что у вас 13, 14 и 15. Типа это
And as a corollary,
задача. И вторая часть
that is
там тоже, в принципе,
inner horn, inner home of Quasicategories.
это первое, в принципе, самое первое. В этом смысле.
So we take S to be
Ну,
arbitrary
это на самом деле больше
simplicial
скорее
set
про решать, если
and D to be a quasi-category. Then the functional complex of maps from our simplicial set to quasi-category is itself quasi-category. How do we do this? Well, we got such a map from that is just a so give me a moment, where did it come from? So we applied, we've just applied Cyrill theorem.
То есть идея была, как это решать? Это которая четвертая, это стереометрия, там по идее.
We've applied Cyrill theorem, this kind of relation to the functional complex. So I'm sorry. And we've got everything broken. We've closed window accidentally. Nevertheless, let's continue. So where did we stop? We have such thing. Like this. And that is the same as if we interchanged some variables. So if we mapped from S to such a space, that would therefore also be a trivial configuration. And this statement is a corollary of our other result, basically that for if we got a map from here to here and it is trivial configuration, then taking the set of maps from some space induced by well, you see, then taking the map of induced map of functional complexes is also a trivial configuration, and we are done, and we got that space of maps from any simplicial set, in particular of quasicategory to quasicategory is itself a quasicategory. Okay. And I think I'm almost done. I want also to give a definition of endomorphism. But why do I want? Because I want to move further on Kan complexes, considering them as a modulo all our imprecises in the establishing of equivalence between infinity group weights and Kan complexes, and also like a homotopy hypothesis that infinity group weights are model for homotopy types. I want, therefore, model of this, I want to consider Kan complexes as a, so to say, category of Kan complexes as a model for spaces. Okay. And why do I do that? Because we are what we are doing now. We are developing the notion of infinity category. That is a category enriched in homotopy types. We then redefined it as a category enriched coherently in infinity group weights, and at the end we want to define it to be enriched over Kan complexes, and that is kind of more easier. And what we are going to do next is to prove the result that that map of set of maps, space of maps from Kan complex to Kan complex is itself a Kan complex. So Kan complexes are enriched over themselves. That's one direction, and other direction, we, as Misha pointed out the last time, we didn't quite show that quasicategories are in any sense enriched over spaces of any kind, and to fulfill that, I think we will start the next time from simplicial categories recollection, and that's one thing. And the other direction that we will move on is homotopy theory for Kan complexes, and then essentially with some correction, homotopy theory for infinity categories. something like that. So let's define also endomorphisms, which be a part of data for model category of complexes, I believe. And it's defined like so. Morphism of delta op. Set, okay. Then for all like this, such condition holds that T contains all the horns inclusion and that T is weakly saturated. So T is T is generated by inclusion of horns. And what I would say is the easy example. Every endomorphism is in fact monomorphism. And that is because inclusion of horns are monomorphisms themselves. And I think that is all. And I'm ready to answer your questions.
В принципе, сама схема правильная, то есть мы говорим, что если мы не знаем методическое значение, что x равно.
Okay, viewers, are you here? Okay.